For this project, we're going to investigate how linear algebra is used in graphics. Before we can do this, we have to talk about some fundamental principles. In order to make the move to three-dimensional space, we need to look at a few linear algebra concepts. We need to know how to represent points in 3D space, how to move points between different coordinate frames, and how to remove the third dimension when projecting points onto the screen. We can use the Cartesian plane for most of that once we add the z-axis. And the important bit here is understanding orthogonality, which is simply when we want to talk about things that are perpendicular to other things. The concept of handedness refers to the orientation of the z-axis in a given 3D space. If the z-axis conforms to the so-called right-hand rule, then the space is said to be right-handed. Alternatively, if the z-axis points in the other direction, the space is referred to as left-handed. Transformations. A geometric transformation is some function that maps a point or set of points, particularly a matrix, to another point. The most common transformations in computer graphics are translations, rotations, and scaling. In 3 dimensions, rotations and scalings can be represented as a multiplication of a 3x3 matrix by any 3D point. And then there are several types of transformations that we're going to discuss next, starting with linear transformations, and then the identity, scaling, rotations, and shears.
So the first type of transformation we're going to talk about is a linear transformation. So a linear transformation is a mapping V to W between two modules, and that includes vector spaces, that preserves the operations of addition and scalar multiplication. A linear transformation T must obey these two properties. So you have the transformation of alpha times x is equal to alpha times the transformation of x. And what that means is that scaling it before the transformation is the same as scaling it after the transformation. And then the second property is the transformation of sums is equal to the sum of the transformed inputs. So the next two transformation types we're going to talk about is the identity and scale transformations. So the identity transformation is just a linear transformation T that maps every x in vector space V to x itself. And it's represented with a matrix with ones along the diagonal and zeros everywhere else, as seen by I here. So a scale transformation will scale points up or down along each axis. As you can see, it's Sx is equal to Sy equal to Sz equals 1. So it essentially is the same thing as the identity matrix. So the next type of transformation is going to be a rotation transformation. Rotation in 3 dimensions can be a complex topic, but fortunately we don't need to understand all the intricacies to use it. So the first thing you want to consider is rotating around the z-axis. So rotation around the z-axis is the simplest to visualize since the points that lie on the xy plane stay in the xy plane when rotated around the z-axis. So RZ here is a 3x3 matrix that will rotate points around the z-axis. I just want to point out that theta there in sine and cosine is in radians, and a positive angle results in a counterclockwise rotation. So this next slide is just a continuation of rotation transformation. But previously we just looked at rotating around the z-axis, but you might not want to rotate around the z-axis. It might just want to be an arbitrary axis anywhere. So how would you do that? If U is a unit vector representing an axis in space, the following matrix RU that will rotate points around that axis. It's just important note here that theta is in radians and a positive angle results in a counterclockwise rotation when the axis is pointing at you. So the next transformation is a shear transformation. And doing my research, I saw that this type of transformation was one of the less used types for graphics, but it's still used. So what a shear transformation is, it's a transformation that moves points parallel to an axis. Shearing terms arise in the off-diagonal elements of matrices. So the last transformation we're going to talk about is not a linear transformation, and that is translation. So translation moves points along a vector in space. One straightforward way to implement this is with vector addition, where you map P and T, one point to another by adding a vector. So if you consider the formula below, where P is the point and T is the vector that you wish to translate by, you see you add them. But it's actually impossible to build a 3 by 3 matrix that can be multiplied with a point to produce the same translation above. So what you have to do is a fourth dimension trick to handle all the transformations in a unified way. So in order to express the translation with a matrix, we need to add an extra coordinate w, which is equal to 1 to our points. And appending this coordinate lets us augment our transformation matrix with an extra row and add an extra column representing the translation vector.